Good morning, friends. In today's lecture, we will discuss about thermal stress. Now, thermal stress is depends on temperature. If the temperature rise, then thermal stress is rise. So, if we have one bar and we are constantly apply heat at one end, then due to this heat the bar will elongate according to its property. So if it is elongated properly, then there will be no stress, or we can say no thermal stress is produced. But if I provide some restriction at this point, then it will try to elongate at particular distance, but due to restriction it will not. Then thermal stress is developed here, and it will be it may deflect our object in uneven position. So we have to try to reduce this thermal stress by providing appropriate restriction at a distance. Now, if this is a bar fixed at left hand side and it is free in right hand side, if I apply some heat, due to this the temperature is rise and this bar is elongated by delta L. Now first of all we will see the equation of delta L. If there is no restriction or it is freely elongated, then delta L is always proportional to original length of any object and temperature, or we can specifically we can say change in temperature. And if we remove this proportionality limit, then we can put one constant, it is alpha. Alpha is a thermal expansion coefficient. So our final equation is delta L is equal to L alpha T. Now thermal strain, we know the equation of strain is delta L upon L. Now in thermal due to temperature rise, the delta L or length is increased, so delta L is L alpha T. So we will replace delta L with L alpha T. It is L alpha T divided by L. So we can cancel L in numerator and denominator, so we will get alpha into T. So we get thermal strain epsilon is equal to alpha into T. So from that we can find the thermal stress. We know the equation of Young modulus or modulus of elasticity E is equal to sigma upon epsilon, and if we put sigma as a subject, then sigma is equal to E into epsilon, and putting the value of epsilon is alpha T. So our final equation of thermal stress become sigma is equal to E into alpha into T. So this equation we will use in our numerical. So we have two important equation, delta L is equal to L alpha T and sigma is equal to E alpha T. Also another equation is epsilon is equal to alpha into T. Now if we provide restriction at some distance, suppose it is delta, so what the thermal stress or how much thermal stress is produced if we provide restriction at some distance? So it is a case, we can say it is case 2. In case 1 there was a free expansion. In case 2 we provide the restriction at some distance. So in this case delta L will be L alpha T. So it is free expansion and we restrict it after delta. So we can say that the expansion is up to delta, and after that if we restrict our expansion due to thermal, then thermal stress is produced. Now we will divide this equation by L. So it will be delta L upon L is equal to alpha T, as LL is cancelled, and minus delta upon L. So we know that delta L upon L is epsilon, strain. So we get epsilon is equal to alpha into T minus delta upon L. So from that we can get the equation of stress or a thermal stress is sigma is equal to epsilon E is equal to alpha T minus delta upon L into E. So this equation of thermal stress, if we provide some yielding, so if we provide the restriction at distance, it is called yielding. So we have two cases in a thermal stress. So by using this knowledge, we will solve one numerical. So a steel rail is a 15 meter long and is laid at a temperature of 20 degrees centigrade, and the maximum temperature expected is 45 degrees centigrade. So we know that the train rail it is the length of that is 15 meter and normal temperature is there is 20 degrees centigrade and maximum temperature is 45 degrees centigrade. So our temperature difference is 25 degrees centigrade, so we will use T is 25 degrees centigrade, and length is 50 meter and we will use it in mm, so it will be 15,000 mm. Now we have to find the minimum gap between two rail to be left so that the rail do not develop. What is that mean? If we provide sufficient gap between two rail, then due to temperature rise it will expand to certain point and this gap will be filled. So there will be no development. Development means this type of curve is not generated in this rail. So we can say there is no development. For that we have to provide sufficient distance. So we know the equation of delta L in a thermal stress is L alpha T. We know the L, and alpha is thermal coefficient, thermal expansion coefficient is given. It is 12 into 10 raised to minus 6 per degree centigrade. So and T is 25 degrees centigrade as maximum temperature is 45 degrees centigrade and initial temperature was 20 degrees centigrade. So by multiplying this quantity we get delta L is 4.5 mm. So if we provide 4.5 mm gap between these two rail, then there will be no development of thermal stress in rail. Now second case is if stress develop is 40 megapascal, what is the gap left between the rail? So we can here they said that the stress developed stress is already developed, it is 40 megapascal. So what will be the gap? So we know the equation of stress is sigma is equal to, and here they said that we have to find the gap and stress is already developed, so we have to use this stress when yielding is applied. So we will this equation sigma is equal to alpha into T minus delta upon L into E. Now stress is given in megapascal, 40 megapascal. We all know that the megapascal, 1 megapascal is equal to 1 Newton per mm square. So 40 megapascal is 40 Newton per mm square. And we are putting the value of that. Sigma is equal to 40. Alpha is given, it is 12 into 10 raised to minus 6. T, change in temperature, is 25 degrees centigrade, minus delta, that we have to find if 40 megapascal stress is generated. Then L is 15,000 mm. Then Young modulus also is given, it is 200 into 10 raised to 3. So by solving this equation, we get delta is equal to 1.5 mm. So this is the example. If the thermal stress is developed 40 megapascal, then this much gap is required to expand this rail. Okay, so this is an example of thermal stress, and it is asked in GTU in 7 marks, and it is important question. Okay, thank you.